4 light-years does not sound like very much. On a map of the galaxy, it is almost nothing at all, a tiny step beyond the edge of home. And yet between us and that nearest stellar neighbour lies a gulf so deep that whole human lifetimes would vanish inside the crossing. What makes it even more tantalising is that this nearby system is not empty. It contains worlds, possibilities, and just enough familiar hints to stir the oldest instinct we have, the urge to go. But the closer astronomers look, the stranger it becomes, as though the nearest place we might dream of reaching has been built to test every assumption we carry with us. Just beyond our solar system lies the closest known collection of stars to Earth, a system we call Alpha Centauri. To say it is nearby is true only in an astronomical sense. In any human sense, it is still staggeringly remote. Light itself, moving at the fastest speed the universe allows, takes more than 4 years to make the journey. Spacecraft built with our present technologies would need far longer than that. Some would need tens of thousands of years. Even so, Alpha Centauri has held the imagination of astronomers for more than a century, because it occupies a very unusual position in our minds. It is not merely another star system. It is the first one beyond our own that feels close enough to tempt us. What makes that temptation stronger is the structure of the system itself. Alpha Centauri is not a single star. It is a triple star system made up of 3 suns bound together by gravity. 2 of them, Alpha Centauri A and Alpha Centauri B, form a bright binary pair. These are both broadly sun-like stars, orbiting a common centre over a period of just under 80 years. Seen from southern latitudes on Earth, they appear bright enough that, to the naked eye, they blend into what looks like a single brilliant point. In fact, they are among the brightest stars in the night sky. But the real fascination today lies with the third member of the system, Proxima Centauri. It is smaller, dimmer, and far harder to see. It was not identified until the early 20th century, long after the bright binary had already been known. In 1915, the Scottish astronomer Robert Innes compared photographic plates and noticed that a faint point of light had shifted position over time. That motion closely matched the motion of the Alpha Centauri pair. After further study, it became clear that this was no unrelated background star. It was a third companion, and remarkably, it was even closer to the Sun than the bright binary stars themselves. That discovery alone would have guaranteed Proxima Centauri a special place in astronomy. It instantly became the nearest known star to our solar system and, at the same time, one of the faintest stars then known. The paradox was irresistible. The closest star beyond the Sun was not a brilliant beacon, but a dim ember, and the surprises did not stop there. In the middle of the 20th century, astronomers discovered that Proxima was a flare star, a type of star capable of violent eruptions of magnetic energy. At the time, it was one of the most active examples known. So the nearest star to us turned out not only to be dim and elusive, but also erratic, unstable, and energetic in ways that made it scientifically irresistible. Today we know that Proxima Centauri is a red dwarf, a main sequence star far smaller than our Sun. Its mass is only a little over 1/10 of the Sun's. Its diameter is only a small fraction as large. And yet small does not mean simple. In some respects, Proxima is more intense than the Sun in all the ways that matter to a nearby planet. Because of its low mass, the interior of the star is thought to be fully convective. Material inside it churns throughout the entire star, rather than being divided into more stable internal layers. That helps generate magnetic fields, and those magnetic fields can release pent-up energy in sudden flares. These flares are not minor surface ripples. They can blast radiation across the electromagnetic spectrum, including high-energy ultraviolet light and X-rays. Observations of Proxima have shown that its brightness can change dramatically and unpredictably. In 2019, astronomers recorded the brightest flare ever seen from the star. Even in quieter periods, its baseline X-ray output is strikingly high when you remember how small and cool the star is compared with the Sun. And during flares, that activity can surge by enormous factors. A world orbiting close to such a star would not be basking in a gentle red twilight. it would be living under a sky prone to sudden violence. And close is exactly where such a world would need to be. Red dwarfs are faint stars. To receive enough warmth for liquid water to exist, a planet must orbit very near them. That creates one of the central tensions of the entire search for habitable exoplanets. The most common stars in the galaxy are red dwarfs. There are vast numbers of them, and many appear to host planets. At first glance, that sounds like excellent news for life. But the same trait that makes them abundant also creates a trap. If a planet is close enough to be warm, it is close enough to be battered by stellar flares, star-driven particles, and powerful magnetic effects that may slowly strip away the very atmosphere life would need. That is why Proxima Centauri became such a magnetic target for astronomers. It is close. It is active. It belongs to the nearest star system we know. And it is a red dwarf, the class of stars around which many potentially temperate planets are expected to exist. For years, researchers searched the star for signs of orbiting worlds. The task was difficult because Proxima itself is noisy. Flares and stellar activity can mimic or obscure the tiny signals astronomers use to infer the presence of a planet. Yet the search continued because the prize was extraordinary. To find a planet around the nearest star would not simply add one more exoplanet to a growing catalogue. It would define the first truly plausible destination for a future interstellar mission. Meanwhile, Proxima's place inside the Alpha Centauri system added another layer of intrigue. The star lies about 4.24 light-years from Earth, making it slightly closer to us than Alpha Centauri A and B. Yet it remains gravitationally bound to them, orbiting the central pair over a timescale of roughly 500,000 years. In other words, this is not just the nearest star to the Sun, it is the nearest member of the nearest stellar system. How Proxima ended up in that arrangement is still uncertain. It may have formed alongside the binary stars from the same original material, which would imply a shared chemical history. Or it may have been captured later, drawn into the system through gravitational encounters, and gradually settled into its current path. Either scenario is dramatic. Either way, Proxima is part of a larger cosmic family, though one bound together across distances almost impossible to picture. The deeper astronomers looked, the more Proxima felt like a concentrated version of a much larger story in modern astronomy. The universe was no longer a place where planets belonged only to our own neighbourhood. By the early 21st century, exoplanet discoveries had begun to transform our picture of the galaxy. Thousands of worlds were being detected around distant stars. Some were giant gas planets orbiting scorchingly close to their suns. Others were rocky worlds that seemed more familiar. And increasingly, attention turned toward one special category: planets that might sit in a habitable zone, the region around a star where temperatures could, in principle, allow liquid water on a planet's surface. That phrase, habitable zone, has an almost magical pull to it. It suggests comfort, balance and possibility. But it can also mislead. A planet can orbit within a habitable zone and still be utterly hostile. Liquid water requires more than distance from a star. It may require an atmosphere thick enough to sustain pressure, a climate stable enough to avoid runaway extremes, and protection from radiation strong enough to preserve chemistry over long periods. The Earth sits in the Sun's habitable zone, yes, but so does Venus in a broad sense, and Venus is an inferno. Mars also brushes the outer edge of that favourable region, yet today it is dry and cold. Being in the right neighbourhood does not guarantee being a second Earth. Even so, when the search around Proxima Centauri began to produce anomalies that could not easily be explained by stellar activity alone, excitement was inevitable. By the mid-2000s, astronomers had already been hunting for planets around the star without success, but they persisted. Observations from the European Southern Observatory in Chile eventually revealed patterns in the star's motion that hinted at the tug of an unseen companion. In early 2016, an intensive observing effort known as the Pale Red Dot campaign set out to test that possibility, with coordinated observations from multiple instruments and teams around the world. Later that year came the announcement that changed the conversation. Astronomers had discovered Proxima Centauri b, a planet orbiting the nearest star to the Sun. It appeared to have a minimum mass close to Earth's. More importantly, it orbited within Proxima's habitable zone. Suddenly, the nearest star was no longer just a fascinating red dwarf. It was the host of a potentially rocky world, receiving just the kind of stellar energy that made people imagine oceans, clouds, and perhaps even life. The headlines came quickly, because the symbolism was too powerful to resist. The nearest star had given us a planet that looked, at least from a great distance and with very incomplete information, like a possible cousin of Earth. That was the hopeful reading. The harder reading began almost immediately. Proxima b orbits about 20 times closer to its star than Earth does to the Sun. It circles Proxima in just over 11 days. That orbit places it in the right temperature zone only because Proxima itself is so faint. But it also places the planet deep inside the region where stellar flares and radiation are most dangerous. Estimates suggest that a world in that position could receive many times the ultraviolet and X-ray dose that Earth gets from the Sun. Over immense stretches of time, that kind of assault may erode an atmosphere, especially if the planet lacks a strong magnetic field. And then there is the question of rotation. A planet so close to a small star is likely to become tidally locked. One side would perpetually face the star, while the other would remain in endless night. That does not automatically rule out habitability, but it changes everything. Weather patterns, atmospheric circulation, surface temperatures, and the long-term stability of any water all become more complicated. A thick atmosphere might redistribute heat and soften the extremes. A thin one might allow one hemisphere to bake while the other freezes. Without direct imaging, all of this remains uncertain. We know the planet is there. We know its orbit, but the surface itself is still hidden from us. That uncertainty is part of what makes Proxima b so fascinating. It sits at the exact intersection of discovery and ignorance. Close enough to matter intensely, but distant enough to remain mostly unknown. It may be a battered, airless rock scorched by radiation. It may be a tidally locked world with a narrow ring of temperate conditions between permanent day and permanent night. It may once have held more promise than it does now. It may never have resembled Earth at all. And yet, because it is the nearest exoplanet of real interest, it has become a symbol of something larger than itself. It stands for the first horizon beyond the solar system that feels not merely imaginable, but targetable. That is why Proxima Centauri does more than sit quietly in astronomical catalogues. It provokes plans. It invites speculation about flyby probes, laser-driven sails, and missions that would try to cross interstellar space within a human lifetime. It pulls in astronomers, engineers, dreamers, and billionaires for the same reason. Distance alone is no longer the only barrier. Now there is a place on the other side of that distance. A real planet. A real target. A real reason to ask not only whether life might exist elsewhere, but whether we could ever reach the nearest world that made the question feel urgent. And as soon as that possibility appears, the next problem comes into focus. Finding a world is one thing. Understanding whether it could actually welcome life or endure our arrival is something else entirely. Around Proxima Centauri, every hopeful clue seems shadowed by a warning. The nearest promising world may also be one of the harshest, which means before we can talk seriously about going there, we have to confront the star it lives beside and the damage that star may already have done. If Proxima b were orbiting our Sun, the discussion would be over almost immediately. It would be far too close, whipped by heat, and plainly unfit for anything resembling Earth. But Proxima b does not orbit a star like ours. It circles a dim red dwarf, a star so faint that to receive even a modest amount of warmth, a planet must cling to it at an almost unnerving distance. That is what makes the planet so compelling. In one sense, it appears to sit in the right place. In another, it may sit in exactly the wrong environment for life to endure. The discovery itself was enough to electrify astronomy. A rocky world, at least a little more massive than Earth, orbiting the nearest star to the Sun. Not a distant abstraction buried in a catalogue, but a real planet around the first star system beyond our own. Its orbital period is only about 11.2 days, which tells you immediately how tight that orbit must be. Proxima b hugs its star at a distance far smaller than Mercury's from the Sun. And yet, because Proxima Centauri is so much dimmer than our star, that tiny orbit places the planet inside what is often called the habitable zone, the region where liquid water might be possible under the right conditions. That phrase carries enormous emotional weight. Habitable zone. It sounds almost like a verdict. It invites the imagination to rush ahead and fill in the missing details with clouds, seas, continents and weather. But the phrase means much less than it seems to. It only describes the amount of stellar energy a planet receives. It does not tell us whether the planet has an atmosphere, what that atmosphere is made of, whether liquid water actually exists, whether the surface pressure is high enough to support it, whether the planet's chemistry remains stable long enough for anything living to emerge, or whether the star itself is blasting the whole world so violently that any fragile beginning would be erased again and again. That is the central tension surrounding Proxima b. On paper, it looks tantalizingly close to a familiar idea. In practice, almost every detail we can infer about its environment pushes in the opposite direction. Proxima Centauri is not merely active in the casual sense that it has weather, it is magnetically restless. Its flares throw out strong bursts of ultraviolet radiation and X-rays, and because Proxima b orbits so close to the star, it would receive that punishment at intimate range. Estimates suggest the planet may be exposed to 10 to 60 times the ultraviolet and X-ray radiation that Earth receives from the Sun. That is not a marginal difference. It is the kind of difference that begins to reshape whether a planet can keep an atmosphere at all. Atmospheres are easy to take for granted because on Earth they are part of the background of existence. You do not see pressure. You do not usually notice climate regulation happening. You do not wake up each morning grateful that the sky is helping to shield you from radiation. But an atmosphere does all of that. It helps maintain surface conditions in which liquid water can persist. It redistributes heat. It protects chemistry from being sterilized by space weather. It allows weather systems and climate cycles to exist in forms that can remain relatively stable over geologic time. Remove too much of it, or alter it too violently, and a planet can become hostile long before its orbit ever changes. For Proxima b, that atmospheric question looms over everything. The planet may once have possessed volatiles, gases, perhaps even substantial reserves of water, but if the star spent long periods bombarding it with radiation and energetic particles, that material may not have stayed in place. High-energy radiation can break molecules apart in the upper atmosphere. Stellar wind can then help carry lighter elements away into space. Over immense timescales, a world that begins with promise can be stripped down to something much harsher. A habitable zone planet without a durable atmosphere is not really habitable in any familiar sense. It is simply well positioned to lose what it needed. And we do not know whether Proxima b had enough protection to resist that erosion. On Earth, our magnetic field acts like an invisible shield, deflecting a portion of the charged particles streaming outward from the Sun. It is not perfect, but it matters enormously. A strong magnetic field helps reduce atmospheric loss and softens some of the worst consequences of stellar activity. The problem for Proxima b is that the same close orbit that puts it in a temperate energy range may also have slowed its rotation and weakened the conditions that generate a magnetic field in the first place. That brings us to one of the planet's most famous and most unsettling possibilities. Proxima b is very likely tidally locked. That means one hemisphere may always face the star while the other remains in permanent darkness. The same face to the same sun, endlessly. We already know examples of this kind of gravitational arrangement closer to home. Our moon is tidally locked to Earth, which is why it always shows us the same side. Around a dim red dwarf, planets in close orbits are especially vulnerable to that outcome. Over time, tidal forces can rob a planet of rotational freedom until it settles into a locked state. At first glance, that seems catastrophic. It is easy to imagine a blazing dayside and a frozen nightside, a world split into extremes too severe for life or comfort. And indeed, that may be close to the truth if the atmosphere is thin or absent. In that case, heat would not be transported efficiently from the illuminated hemisphere to the dark one. The star-facing side could become intensely hot, while the far side plunges into permanent cold. Any water vapour moving into the dark hemisphere might freeze there, potentially becoming trapped as ice. The planet as a whole could become dry, stark, and climatically unstable in the ways that matter most. But tidal locking is not always a total death sentence. If Proxima b possesses a sufficiently thick atmosphere, then winds and large-scale circulation patterns could move heat around the globe. In that scenario, the contrast between day and night would still be profound, but perhaps not utterly destructive. Some researchers have imagined a ring-shaped zone around the terminator, the moving boundary between light and dark, where temperatures might remain comparatively moderate. Not Earth-like, not gentle, but perhaps survivable in a narrow and peculiar sense. Yet even this more hopeful picture depends on a prior condition we cannot confirm. The planet must first have held onto enough atmosphere to make such redistribution possible. And that returns us to the star. Proxima Centauri does not offer calm, patient illumination. It offers irregular episodes of violence. A thick atmosphere might help buffer the surface from those flares, but repeated stellar outbursts could also erode the same shield over time. The closer you examine the planet, the more the questions begin to stack on top of one another. Could it have formed with abundant water? If so, did it keep it? Could it have retained a dense atmosphere? If so, for how long? Could a tidally locked world still host a habitable region? Perhaps, but only if enough of the earlier answers turn out to be favourable. Proxima b lives inside a chain of contingencies, and we currently know almost none of them with confidence. Its origin only deepens the uncertainty. If Proxima b formed where it is now, very close to the star, then the early environment may have been even more hostile than the present one. The planet would have evolved rapidly under intense irradiation and stronger impact conditions, perhaps with less water available from the start. But some scientists argue that the amount of material expected so close to Proxima Centauri may not have been sufficient to build the planet there in the first place. In that view, Proxima b may have formed farther from the star, where conditions could have been different, and then migrated inward over time. That would change the story significantly. A world born farther out might have gathered more volatile compounds, including water, before moving into its current orbit. Yet migration does not resolve the problem so much as relocate it. Even if the planet formed in a colder, richer region of the system and drifted inward later, it still ended up where it is now, locked close to a flare star. Any earlier bounty of water or atmosphere would still have faced the same long exposure to radiation once the planet settled into its current path. In some versions of that history, migration improves the starting conditions, only to make the eventual loss more tragic. A world that once had more of what life needs may have been delivered directly into an environment capable of taking it away. There are other clues, though they too are ambiguous. Proxima b is thought unlikely to host long-lived moons because stable lunar orbits are difficult to maintain so close to the parent star. That matters because moons can influence planetary evolution in subtle ways. On Earth, our moon helps shape tides and may have contributed to long-term stability in ways still debated. Proxima b may have had no such companion. It may have developed in relative isolation under a very different dynamical regime from the one that shaped our own world. Once again, every path leads back to the same conclusion. Even when the planet looks superficially Earth-like in size, its deeper history may be alien in almost every important respect. So what might its surface actually look like? The honest answer is that we do not know. We have not directly imaged the planet in any detailed sense. There is no photograph waiting to settle the matter. The possibilities range from a dry, rocky surface blasted by radiation to a frozen world with ice locked away in darkness. Some models allow for a global ocean or extensive water coverage, though that appears increasingly difficult to sustain under the harshest assumptions. Other possibilities are stranger still, a planet with buried water beneath a hostile exterior, perhaps something closer in spirit to an icy moon than to Earth. The world may have coastlines, or none at all. It may have weather of a very unfamiliar kind. It may have no exposed liquid water anywhere on the surface. And yet for all this uncertainty, Proxima b remains extraordinarily important. Not because it is confirmed as a second Earth, but because it forces us to sharpen what we mean when we talk about habitable worlds. It takes the most emotionally potent category in exoplanet science and puts it under pressure. What counts as promising? What counts as survivable? How many of our assumptions come from habit rather than evidence? Around Proxima b, the dream of another Earth becomes more disciplined. The romance of nearness collides with the physics of red dwarfs, atmospheric escape, and tidal locking. Suddenly, the real story is not that we found a nearby paradise. It is that the nearest potentially temperate world may already demonstrate how hard genuine habitability is to achieve. That difficulty is precisely why Proxima b has become more than a planet. It is a test case, a warning, a target. It concentrates almost every major question in modern exoplanet science into one place. Can life survive around red dwarfs? Can a tidally locked world remain clement? Can atmospheres endure beneath relentless flare activity? Can a planet that seems broadly Earth-sized actually be anything like Earth when all the hidden conditions are different? We do not yet have the instruments to answer those questions directly from the surface, and that gap between importance and ignorance is what makes the system so powerful in the human imagination. Because once you have a nearby world that is both compelling and uncertain, the next instinct is not just to observe it more carefully, it is to go. To imagine probes, flybys, cameras and instruments crossing the darkness and finally showing us what has so far existed only in data and theory. The mystery of Proxima b does not end with whether it can support life. It opens into a larger ambition. If this is the nearest serious target beyond the solar system, then everything depends on how far we are willing to push our technology to see it up close. And as that ambition grows, another set of worlds around the same star begins to come into view, along with the unsettling realization that even our nearest stellar neighbour may be more complex and more uncertain than a single planet can capture. 6 years after the discovery of Proxima b, astronomers announced another planet in the same system, and once again the nearest star to the Sun became even harder to simplify. This new world, Proxima d, is thought to be one of the lightest exoplanets ever detected. Its estimated mass is only about 1/4 of Earth's. That alone makes it extraordinary, because planets so small are notoriously difficult to find. Their gravitational pull on a star is tiny, almost lost inside the noise of stellar activity and instrumental limits. To detect one around a flare star as unruly as Proxima Centauri was not merely another addition to a list. It was a sign of how far exoplanet astronomy had advanced. But Proxima d did not make the system feel more hospitable. If anything, it sharpened the contrast between detectability and desirability. The planet orbits much closer to the star than Proxima b, completing a year in just over 5 Earth days. That places it far inside the inner edge of any plausible habitable zone. Whatever else Proxima d may be, it is almost certainly too hot and too exposed to offer anything like a temperate environment. Its importance lies elsewhere. It tells us the system is not built around a single intriguing world. It is, or at least may be, a compact planetary architecture shaped under conditions very different from those that formed our own solar system. That matters because planetary systems are stories of formation. Each planet carries information not only about itself, but about the disk of gas and dust from which it emerged, the migrations it may have undergone, the gravitational interactions that sculpted its orbit, and the violence it endured in the early eras of its star. A tiny planet like Proxima d, close to the star, and a somewhat larger world like Proxima b farther out, suggest a system with structure, perhaps even a history of rearrangement. The more pieces we add, the less Proxima Centauri looks like a lone red dwarf with a single famous companion. It begins to look like a genuine planetary system, compact, dynamic, and still only partly visible to us. And then there is the most controversial member of the family, Proxima c. Unlike Proxima d, this planet has not taken its place as cleanly in the scientific picture. Evidence for it has emerged through subtle signals in the star's motion, suggesting a much more distant world with an orbital period of around 5 Earth years. If it exists, it appears to be significantly more massive than Earth, perhaps several times Earth's mass, placing it in the category often called a super-Earth or mini-Neptune, depending on its composition. But the detection has remained disputed. Proxima Centauri is an active star, and activity can imitate planetary signals with unnerving skill. A pattern that looks like a planet can sometimes dissolve into stellar noise when the data are reanalyzed. That uncertainty is not an embarrassment. It is one of the most honest features of exoplanet science. From the outside, discoveries can seem clean and cinematic. A planet is found, given a name, and added to the map. In reality, the process is often messy. Signals appear, vanish, strengthen or weaken, depending on how observations are modelled. Different teams may interpret the same data differently. Some candidates survive repeated scrutiny and become secure. Others remain suspended in an awkward space between possibility and proof. Proxima C lives in that space, which makes it scientifically valuable even before its existence is settled. It reminds us that the nearest star system is still not something we know in a complete or comfortable way. If Proxima C is real, then the system becomes more interesting again. A more distant and more massive planet would imply a wider diversity of formation pathways around Proxima Centauri than once assumed. It might also complicate our ideas about migration, orbital stability, and the long-term history of the system. A world several times Earth's mass, orbiting farther out, could represent a different category of planet entirely from Proxima B and D. It might hold onto a thick, gaseous envelope. It might resemble a scaled-up rocky world. It might have formed beyond a frost line and remained there. Or it might tell us that compact red dwarf systems can produce planetary arrangements far more varied than the one we see around our own star. Yet even the uncertain nature of Proxima C reinforces the deeper theme. The closer we get to the nearest stellar neighbour in terms of data and attention, the less it behaves like a simple destination. It behaves like a puzzle. Proxima B may be the most emotionally potent world in the system because it sits near the habitable zone. Proxima D proves we can detect astonishingly small planets around nearby stars. Proxima C, if confirmed, would widen the architecture further and remind us how much can still hide in even the most observed systems. Together they transform Proxima Centauri from a single planetary headline into a compact laboratory for the biggest questions in exoplanet science. That is one reason the Alpha Centauri system occupies such a disproportionate place in future mission concepts. In a galaxy full of stars, why do we keep returning to this one? The obvious answer is distance. At just over 4 light-years away, it is the nearest opportunity we have. Every other candidate destination adds distance and therefore delay, risk, and technological burden. But there is something more than convenience involved. The system combines nearness with genuine scientific urgency. It contains Sun-like stars in Alpha Centauri A and B, a magnetically volatile red dwarf in Proxima Centauri, and at least one confirmed rocky exoplanet of tremendous interest. It offers not one question, but many. Could life exist around red dwarfs? Do nearby Sun-like stars host undiscovered planets too? How different can planetary systems be, even within the same broad stellar family? Those questions are powerful enough that they have helped push interstellar travel, long dismissed as distant speculation, back into serious conversation. For most of modern history, travel to another star belonged more to fiction than engineering. The distances were not merely large, they were crushing. Voyager 1, one of the fastest and most far-travelled spacecraft ever built, would need tens of thousands of years to get to Alpha Centauri if it were aimed in that direction. Human beings are not built for projects measured across civilizations, so for interstellar travel to enter realistic discussion, something radical had to change. Either our propulsion methods had to become vastly more powerful, or our spacecraft had to become unimaginably smaller. That is where one of the boldest modern concepts enters the story. Breakthrough Starshot, announced in 2016, proposed something closer to an engineered leap than an incremental improvement. Instead of sending a massive spacecraft burdened by fuel, shielding, and conventional systems, the idea was to send tiny probes, wafer-thin spacecraft attached to light sails. Those sails would be driven not by onboard propulsion, but by a powerful array of Earth-based lasers. By concentrating enormous energy onto the sail, the probes could, in principle, be accelerated to a meaningful fraction of the speed of light. The target speed often discussed is around 20% of light speed, fast enough to reach Alpha Centauri in roughly 20 years. The audacity of the idea is hard to overstate. At that speed, a probe no larger than a chip could cross interstellar space in the time it takes a human being to move from youth into middle age. Compared with every previous notion of star travel, it felt almost absurdly fast. That is why the concept attracted attention from scientists, technologists, and wealthy patrons, including figures such as Yuri Milner, Stephen Hawking, and Mark Zuckerberg. Not because the engineering was easy, but because for the first time in a long while, someone had described a path that did not require miracle physics. No warp drives, no wormholes, just a terrifying concentration of known physics pushed to its edge. But known physics does not mean solved engineering, far from it. To make a project like that work, the sail would need to survive extraordinary acceleration. The lasers would need precision and power on a staggering scale. The tiny spacecraft would need to navigate interstellar dust at relativistic speeds, where even a grain of material could become destructive. It would need to survive the deep cold, communicate across light years, and perform useful science during a flyby that might last only a brief window as the target system rushed past. Then there is the problem of targeting itself. Which star do you aim for? Alpha Centauri A? Alpha Centauri B? Proxima Centauri? If the most interesting known planet is Proxima B, then the system's faintest and most active star becomes the most compelling destination. That choice is not trivial. Alpha Centauri A and B are bright, sun-like, and easier to imagine in familiar planetary terms. For years, astronomers have searched both stars for signs of planets. Claims have appeared and then been questioned. Hints have surfaced, then dimmed. So far, no planet around either star has acquired the same confidence or cultural force as Proxima B. That means the red dwarf, difficult and hostile though it may be, remains the most scientifically tempting branch of the system. It is the place where the first true interstellar reconnaissance might reveal not just a distant point of light, but a world. And that possibility changes the emotional texture of the whole field. For centuries, other stars were lights. Then they became suns. Then some of them became hosts to planets. Now, in one extraordinary case, the nearest one hosts a planet close enough and important enough that people can sketch serious mission architectures to see it. We are still nowhere near launching such a mission. The obstacles are immense, and many may prove harder than the most optimistic proposals suggest. But a threshold has been crossed all the same. Interstellar travel is no longer discussed only in the language of pure fantasy. It is beginning to acquire budgets, roadmaps, technical papers, and failure modes. That is what happens when the unknown gets just close enough to provoke action. Still, the deeper irony remains. The more Proxima Centauri motivates our dreams of going outward, the more it also teaches caution. Its known planets do not yet offer reassurance. They offer challenge. A small, scorched world very close in. A more temperate but deeply uncertain rocky planet farther out. A possible outer companion that may not exist, or may complicate the picture further if it does. This is not a system inviting us in with open arms. It is a system daring us to understand it. And as that challenge broadens beyond one nearby star, it leads directly into a larger cultural obsession that Proxima B only intensified. Once you discover even a single seemingly Earth-sized world around the nearest star, the natural next question is impossible to avoid. If there is one nearby, how many more are out there across the galaxy? But that question contains a hidden trap, because the search for another Earth has always been driven as much by longing as by evidence, and the phrase Earth 2.0 can make the universe sound far simpler than it really is. The hunt for exoplanets changed astronomy so quickly that within a single generation, what once sounded speculative became almost routine. For most of human history, planets beyond our solar system were matters of inference, philosophy, and imagination. Then, beginning in the late 20th century and accelerating into the 21st, they became data. One by one at first, then in torrents, worlds started appearing around other stars. Giant planets came first because they were easiest to detect, then smaller ones, then rocky ones, then worlds that seemed to sit at roughly the right distance from their stars for liquid water to exist. And with that, a phrase began to spread far beyond astronomy itself: Earth 2.0. It is an alluring phrase because it compresses a vast emotional desire into two simple words. We are not just looking for planets. We are looking for familiarity. We are looking for reassurance that what happened here might happen elsewhere, and perhaps often. We are looking for a place that feels less like a hostile alien world and more like a second home waiting in the dark. The phrase does powerful work in the imagination because it suggests that Earth is not singular, only first. It suggests that if we keep searching, we will eventually find another blue world with air, water, weather, and perhaps even life looking back under another sky. But phrases like that can distort as easily as they inspire. They encourage us to imagine habitability as a simple checklist, or worse, as a label that can be earned from a distance with very little evidence. A planet gets the right amount of starlight, and suddenly it enters the public conversation as potentially Earth-like. Yet Earth is not just a planet at the right distance from a star. It is the product of an immense number of conditions working together across billions of years. It has the right atmosphere, the right long-term stability, the right protection from radiation, the right chemistry, the right gravity for a human body, and a geological history that did not collapse into permanent catastrophe. Remove several of those elements, and Earth stops being Earth very quickly. That is why the flood of exoplanet discoveries has been both revolutionary and humbling at the same time. On one hand, it has shown us that planets are everywhere. The old assumption that our solar system might be unusual simply in having planets no longer survives. Worlds seem to be a normal byproduct of star formation. That realization alone changes the scale of the universe as a place of possibility. On the other hand, the more worlds we find, the more we are forced to admit how little a first detection usually tells us. A mass estimate, an orbital period, a rough distance from the host star, perhaps a size if the geometry is favourable. Those are meaningful facts. They are also fragments. The habit of filling in the rest is understandable. Human beings are pattern-making creatures, and we are especially vulnerable to projection when the missing information happens to align with our deepest hopes. A rocky planet in a habitable zone begins to collect imagined qualities almost instantly. Oceans appear in concept art, clouds gather, colours soften. It starts to feel emotionally inhabited long before science can justify that feeling. But the actual physics remain indifferent to our instincts. A planet can sit in the habitable zone and still be crushed beneath a toxic atmosphere, sterilised by radiation, stripped of air, frozen under permanent cloud, or trapped in climate cycles that never allow long-term surface stability. Venus and Mars should have cured us of simplistic thinking long ago. In broad terms, both occupy regions that are not outrageously far from what we call the Sun's habitable zone. Yet one became a planet with a dense carbon dioxide atmosphere and surface temperatures hot enough to melt lead, while the other lost much of its atmosphere and much of its accessible surface water, becoming a dry and frigid desert. Neither outcome is remotely Earth-like. Those two nearby examples are crucial because they show that habitability is not some neat geometric ring drawn around a star. It is an evolving planetary state, vulnerable to chemistry, geology, atmosphere, radiation, and history. Once you understand that, the phrase Earth 2.0 starts to feel less like a scientific category and more like a cultural shortcut. It does not mean scientists are being careless when they talk about promising planets. It means the wider conversation often compresses many layers of uncertainty into a cleaner and more hopeful picture than the evidence deserves. The real work of planetary habitability is messier. It asks not only whether water could exist in principle, but whether it can remain stable in practice. Not only whether a planet is rocky, but whether it is geologically active in useful ways. Not only whether it has an atmosphere, but whether that atmosphere protects more than it destroys. This is why the search for another Earth has steadily matured into something more cautious and more intellectually demanding. Early on, simply proving that planets existed around other stars was a triumph. Then the question became how common they were. Then whether rocky planets were common. Then whether some lay in habitable zones. Now the standards are becoming stricter, because the easy categories are no longer enough. Astronomers increasingly want to know about atmospheres, cloud cover, surface pressure, temperature distribution, and chemical disequilibrium. Any clues that might suggest not just a planet that exists, but a planet that works in a way compatible with life. And even that is more complicated than it first appears. Life itself may not require the same narrow conditions that human beings find comfortable. Microbial life, for example, can survive in environments on Earth that would kill us quickly. So when we talk about habitable worlds, we are often blending different questions together. Habitable for what? For microbes? For complex multicellular life? For future human visitors? For stable surface oceans over billions of years? Those are not the same question, and a planet that answers one favourably may answer another with a decisive no. Much of the confusion in public discussions comes from treating them as interchangeable. A world like Proxima b illustrates the problem perfectly. It can sound promising because it is rocky and lies in the habitable zone of the nearest star. But that description leaves out the hostility of the star, the uncertainty of the atmosphere, the likely tidal locking, and the possibility that the world has been battered for eons in ways that make surface habitability extremely difficult. The phrase habitable zone is technically relevant, but emotionally misleading. It invites an image more generous than the data support. In reality, many of the planets that seem most exciting at first glance become less comfortable, not more, as we learn to ask better questions. That pattern repeats across the exoplanet catalogue. Again and again, discoveries arrive with an initial wave of enthusiasm, only for deeper analysis to reveal caveats. Some planets are larger than first thought. Some may be gaseous rather than rocky. Some receive the right overall energy, but from stars that behave violently. Some may be locked into strange rotations. Some may never have had the ingredients we are imagining. This is not a failure of the science. It is what science looks like when a field is moving from first discovery into real understanding. The universe is not disappointing us. It is simply refusing to simplify itself for our convenience. And yet the dream persists, for good reason. If there are hundreds of billions of stars in the Milky Way, and many host planets, then even rare conditions may still occur many times. That statistical intuition is powerful. It suggests that somewhere, perhaps many times over, the ingredients might align. A stable star, a rocky planet, a protective atmosphere, long-term climate moderation, liquid water, enough time, enough luck, enough resilience. The problem is not that such worlds must be impossible. The problem is that from our current vantage point, confirming them is extraordinarily difficult. We can infer a world, we can estimate its size, we can sometimes begin to probe its atmosphere, but we are still very far from surveying alien surfaces with the confidence we bring to the planets of our own solar system. That gap between abundance and proof is one of the defining features of modern astronomy. The numbers are growing fast. The certainty is growing more slowly. We know enough to say that planets are common and that some rocky planets exist in potentially temperate orbits. We do not yet know enough to identify true Earth analogues with confidence. In other words, the galaxy is becoming crowded with candidates at the same time that our standards for what counts as genuinely Earth-like are becoming much stricter. That can feel frustrating, but it is actually a sign of progress. The search is becoming more honest. One of the biggest reasons for that honesty is the growing recognition that stars themselves may be the hidden filter. A planet can have the right orbit and still fail because its star is the wrong kind of companion. Some stars are too short-lived, some are too unstable. Some flood nearby planets with radiation. Some force habitable zone worlds into close orbits that alter their rotation and climate beyond easy recovery. This is where the sheer abundance of red dwarfs becomes especially important, because red dwarfs dominate the galaxy numerically, and many of the rocky planets we detect sit around them. At first, that sounds like wonderful news. If the most common stars in the galaxy host vast numbers of rocky worlds, then the Milky Way should be full of possibilities. But red dwarfs come with a cruel catch. Their habitable zones are close in, very close. That means the planets we most want to be temperate are also the planets most exposed to flare activity, tidal locking, and atmospheric erosion. Suddenly, abundance begins to look less reassuring. The galaxy may be rich in candidates, while still being poor in truly forgiving environments. And that is where the dream of Earth 2.0 starts to change shape. Instead of asking how many planets look broadly like Earth from a distance, we begin asking how many can survive the deeper forces that make or break habitability. How many avoid early atmospheric collapse? How many keep their water? How many rotate in ways that preserve climate stability? How many orbit stars calm enough to allow surface chemistry to persist over immense spans of time? Those questions do not kill the dream. They make it more rigorous. The irony is that the more carefully we search for another Earth, the more extraordinary Earth itself begins to appear. Not miraculous in a supernatural sense, but increasingly specific. Not just a rock in the right place, but a world that threaded a very narrow corridor through chaos. That does not mean it is unique. It means uniqueness is no longer something we can dismiss with a slogan. If another true Earth exists, we may have to earn that knowledge by learning how most promising worlds go wrong, especially around the stars that dominate our galaxy. Those stars are red dwarfs, and in raw numbers they rule the Milky Way. They are smaller than the Sun, cooler than the Sun, dimmer than the Sun, and vastly more common. If you could drift through our galaxy and count its suns one by one, most of what you found would not be bright yellow stars like ours. You would mostly find these faint red embers, burning slowly and economically for spans of time that can dwarf the current age of the universe. At first glance, that should make them the great hope of the search for life. Long-lived stars offer time, abundance offers opportunity, and if rocky planets are common around them, then the galaxy should seem full of possible homes. That hopeful logic is not wrong, it is just incomplete. Red dwarfs really do matter enormously, because they provide so many chances for planets to form. Their long lifetimes also mean that if stable, habitable conditions can arise around them, those conditions might persist for extraordinary lengths of time. A world circling a red dwarf would not have to worry about its star swelling into a red giant after only a few billion years, the way the Sun eventually will. In principle, such systems could host ancient biospheres, older than anything Earth has yet known. That possibility is one reason astronomers keep returning to them. You do not ignore the most common stars in the galaxy when asking where life might exist. But red dwarfs also concentrate some of the most punishing hazards a planet can face. Because they are faint, the region around them where liquid water might exist is pulled inward to a remarkably tight range. A planet must orbit close to receive enough energy to be temperate. Not somewhat close, extremely close. That changes everything. The same proximity that provides warmth also amplifies every danger the star can impose. Radiation becomes more intense. Gravitational effects become stronger. The atmosphere, if there is one, lives under greater strain. And over time, the star's influence can begin to reshape the planet itself. This is the first great trap of red dwarf habitability. To be warm enough, a world must move into the zone where the star becomes hardest to live with. That is why planets like Proxima b are so difficult to judge. From one angle, they occupy the right orbital region. From another, they are sitting in the blast radius. A temperate orbit around a red dwarf often means a dangerously intimate relationship with a magnetically active star. The same light that makes surface water possible arrives entangled with ultraviolet bursts, X-rays, charged particles, and violent flares that can alter the chemistry of an atmosphere or strip that atmosphere away over time. Young red dwarfs may be especially destructive in this regard. Many of them spend long periods in an energetic, unstable phase early in their lives. During that era, Planets in close orbits can be exposed to intense radiation for immense stretches of time. Even if such a world eventually enters a more moderate epoch, the damage may already have been done. Water can be broken apart, hydrogen can escape to space, atmospheric layers can thin or vanish. A planet may retain its place in the habitable zone on paper, while becoming far less habitable in physical reality. It is possible that some worlds around red dwarfs began with substantial promise, and then lost it before biology ever had a stable chance to begin. Then comes the second trap, tidal locking. A planet orbiting close to a small star is likely to feel strong tidal forces, the same basic phenomenon that shapes tides on Earth and keeps the moon showing us only one face. Over enough time, those forces can slow a planet's rotation until one side always faces the star. The result is a world with permanent day on one hemisphere and permanent night on the other. No sunrise, no sunset, no familiar cycle of warmth and cooling, just a fixed geometry of light and darkness imposed by gravity. This condition is easy to picture and easy to fear. One side may seem doomed to overheat, the other to freeze solid. In the simplest case, that is close to what could happen. If the planet has little or no atmosphere, the illuminated hemisphere may absorb energy until temperatures rise dramatically, while the dark hemisphere becomes a sink of endless cold. Volatiles could migrate and freeze out on the night side. Surface pressure could collapse. The world could become divided into stable extremes too severe for a comfortable planetary climate. The habitable zone would have produced a planet that is not temperate in the human sense at all, but broken into climatically incompatible realms. Yet again, the reality is more subtle and therefore more frustrating. Tidal locking does not automatically make a planet lifeless. A thick enough atmosphere could carry heat around the globe. Winds could move energy from the day side into the cold darkness. Oceans, if present, could also redistribute warmth. Some climate models suggest that tidally locked planets might support habitable conditions in a band or broad region rather than across the entire surface. There could be a permanent substellar region beneath the fixed noon sun, where clouds reflect some incoming energy. There could be an intermediate zone, where temperatures remain mild enough for liquid water. The problem is that all of this depends on an atmosphere robust enough to do the work, and around active red dwarfs, that is exactly what is in doubt. This is why the most promising red dwarf planets often seem to carry their own undoing inside the same conditions that make us notice them. Their closeness to the star allows warmth, but invites tidal locking. Their proximity allows liquid water in principle, but increases exposure to stellar flares. Their stars live for staggering lengths of time, but may spend long early eras in hostile activity. What looks at first like an abundance of opportunity starts to feel more like a gauntlet. A planet does not merely need to land in the right orbital zone, it must also survive everything that being in that zone entails. Kepler 186f offers a useful example of how quickly hope can become more complicated. When it was announced, it drew immediate attention because it was one of the first Earth-sized planets found in the habitable zone of another star. That alone made it historic. It seemed to mark a threshold, proof that a world roughly similar in size to ours could occupy the right region around its star. But the host star is a red dwarf, and once that fact enters the picture, the comforting simplicity begins to fade. The planet's orbit, stellar environment, atmospheric history, and rotational state all become crucial, and many of those things remain uncertain. Kepler 186f is still deeply important. It is also a reminder that Earth-sized and habitable zone are beginnings of a question, not the end of one. The same pattern appears over and over in red dwarf systems. A new planet is found, the size looks encouraging, the orbit seems favourable, the headlines lean toward possibility. Then the deeper questions begin. How active is the star? How old is the system? Has the planet retained a magnetic field? Is it tidally locked? Did it keep its water? Is the atmosphere thick, thin, or absent? The more carefully you ask those questions, the more often the initial optimism gives way to caution. It is not that the planets become uninteresting. If anything, they become more scientifically rich. but they usually become less like the easy fantasy of a second Earth. Proxima b may be the clearest case, because it is both the nearest and one of the most emotionally loaded. It is a rocky planet in the habitable zone of the closest star to the Sun. That sentence almost writes its own mythology. And yet, every mechanism that governs red dwarf worlds presses against the hopeful interpretation. Proximity to a flare star, likely tidal locking, possible atmospheric erosion, uncertain water inventory, unknown magnetic protection. The planet does not fail because one dramatic piece of evidence destroys the dream. It becomes difficult because many smaller uncertainties stack in the same direction. One by one, they lower the confidence that a habitable zone label really means what we wish it did. None of this proves that life cannot exist around red dwarfs. That would be too strong a conclusion, and science does not support it. Life, especially simple life, may be more adaptable than our intuitions allow. Biology on Earth has endured radiation, darkness, dryness, crushing pressure, and astonishing chemical extremes. It is entirely possible that somewhere in the galaxy, a planet around a red dwarf found a stable niche and kept it. Perhaps the atmosphere survived. Perhaps the magnetic field held. Perhaps oceans buffered the climate. Perhaps life emerged not despite the oddity of the world, but by adapting to it. The caution surrounding red dwarfs is not a declaration of impossibility. It is a recognition that the path to long-term surface habitability there may be much narrower than the number of planets alone would suggest. And that distinction matters because red dwarfs dominate the statistics. If they turn out to be poor hosts for durable biospheres, then the galaxy may still contain many planets, while offering fewer truly forgiving environments than simple planet counts imply. Abundance would remain real, but suitability would become rarer. This is one of the great hidden filters in the search for life. A galaxy can be full of rocky worlds, without being full of worlds where chemistry, climate, and time align in the right way. Habitability is not just about how many planets exist. It is about how many avoid being pushed into failure by the stars they orbit. This brings us back to the deeper lesson emerging from the exoplanet era. The more we learn, the less useful simple labels become. Red dwarfs are not good or bad for life in any absolute sense. They are opportunities under pressure. They offer immense numbers of planets and immense spans of time, but they also impose harsh conditions that may exclude many of the worlds we most want to imagine as welcoming. In a way, they force us to grow up scientifically. They make us trade the easy romance of Earth 2.0 for a more disciplined question. What does a planet actually need, not just to look promising from far away, but to remain physically habitable across geologic time? That question grows even sharper once we stop thinking only about microbes, atmospheres, and water, and start thinking about bodies, human bodies. Because a planet may clear every stellar hurdle we have discussed so far, and still turn out to be a place where a person could not live comfortably at all. The star may permit it. The orbit may allow it. The climate may even seem survivable. But if the world's gravity is wrong, then the experience of living there changes from the cellular level upward, and the meaning of a habitable planet changes once again. Gravity is so familiar that we rarely think of it as a condition of life. It feels fixed, natural, almost invisible. You wake up inside it, move through it, build within it, age within it, and only really notice it when it changes, even slightly. But gravity is not just a background setting. It is one of the deepest forces shaping what a planet can be and what a body can endure. When we imagine living on another world, we often picture the sky, the ground, the weather, perhaps the oceans, if there are any. Much less often do we picture the weight of our own bones, the strain on the heart, the effort of standing, the burden carried by every organ with each passing hour. That omission matters because habitability is not only about whether life in general could exist somewhere. It is also about what kind of life, under what physical conditions, and for how long. A planet might have liquid water, a reasonable atmosphere, and a tolerable average temperature, yet still be a miserable or even damaging place for a human being if its gravity differs too far from Earth's. Too little gravity, and the body begins to weaken in ways we already understand from long stays in orbit. Too much gravity, and every ordinary movement becomes more demanding. Circulation becomes harder, joints and bones bear heavier loads, and the simple act of living turns into continuous mechanical labour. We already have one partial glimpse of what low gravity does to us. Astronauts in microgravity lose bone density. Muscles shrink unless they are constantly trained. Fluids shift through the body in unusual ways. The cardiovascular system adapts to a world in which it no longer has to work against the same vertical pull. Eyesight can be affected. Balance changes. Returning to Earth after prolonged time away can make standing and walking feel difficult again. That is with intensive exercise, medical support, and a carefully controlled environment. It tells us that the human body is not built for indefinite freedom from Earth's pull. We are adapted very specifically to one gravitational regime, not to gravity in the abstract. Now imagine the reverse problem. Imagine a planet more massive than Earth, with stronger surface gravity, where every object weighs more and every movement demands more force. Even if the atmosphere were breathable and the temperature acceptable, your body would immediately notice the difference. Lifting your arms would feel harder. Climbing would become exhausting much more quickly. The heart would have to work more to pump blood upward through the body. The lungs might still function, but breathing during effort would feel heavier. Joints would bear greater stress. Falls would be more dangerous. Over time, even a modest increase in gravity could turn ordinary life into a persistent test of endurance. This is where the public language around so-called super-Earths can become misleading. The phrase sounds inviting, almost triumphant, as though we are talking about a larger and perhaps better version of our own world. But many planets in that category may not be Earth-like in the ways that matter most to a human body. A super-Earth simply means a planet more massive than Earth and lighter than the ice giants in our solar system. It tells us little by itself about surface conditions. Some may be rocky. Some may hold thick atmospheres. Some may have deep global oceans. Some may be closer in spirit to scaled-down Neptunes than to anything we would recognise as a terrestrial home. And even the rocky ones may exert gravity well above what human beings could comfortably tolerate for long periods. Kepler 452b is a good example of how a seemingly attractive candidate can become more ambiguous once gravity enters the picture. The planet drew attention because it orbits in the habitable zone of a star somewhat similar to the Sun. It was widely described as one of the most Earth-like planets then known, and in certain broad respects, that reaction made sense. But Kepler 452b is also thought to be significantly larger than Earth. If it is a rocky world, then its surface gravity could be substantially stronger than ours. That alone changes the picture dramatically. A planet can be in a broadly favourable orbit and still be physically punishing to the kind of body we actually have. Proxima b raises a related question from a slightly different angle. Its estimated minimum mass is only a little above Earth's, which sounds encouraging, but mass and gravity are not identical, because the final surface pull depends on both mass and size. A denser planet packed into a relatively compact radius could produce stronger gravity than its mass alone might suggest. And even if Proxima b's gravity turned out to be fairly close to Earth's, that would not rescue it from all the other hazards imposed by its star. This is the point. No single factor decides habitability. Gravity can disqualify a world that looks favourable in other ways, but a reasonable gravity cannot redeem a world being sterilised by radiation or stripped of its atmosphere. Still, the gravitational question matters enormously once the conversation shifts from life in general to human settlement. We can imagine microbes adapting to conditions far outside human comfort. We can imagine ecosystems unlike anything on Earth, built around different atmospheric pressures, different light environments, perhaps even different surface chemistries. But the human body is a narrower instrument. It has limited tolerance for long-term deviation. On a world with much higher gravity, children might develop differently. Pregnancy could become riskier. Injury recovery could slow. Chronic stress on the skeleton and cardiovascular system might shorten healthy lifespan, even if day-to-day survival remained possible. A place need not kill us outright to be a bad home. It only needs to make ordinary life steadily harder. There is a cruel irony here. In the search for habitable planets, larger rocky worlds can sometimes seem attractive because bigger planets may hold on to atmospheres more effectively than smaller ones. More gravity can help a world retain gases over long spans of time. That sounds useful, especially when atmospheric loss is one of the great hazards discussed around red dwarf systems. But the very trait that helps preserve a planet's air can also make that planet less welcoming to our bodies. The same gravity that keeps the atmosphere from leaking away may press too hard on every human system trying to function beneath it. Too little gravity creates its own long-term trap. Mars offers a nearby illustration, though even Mars is not truly low gravity in the same way as a small moon or asteroid. Its surface gravity is a bit more than 1/3 of Earth's. That is enough that you would still feel weight and move in a clearly planetary environment, but over long periods it might not be enough to preserve human health in full. We do not yet know all the consequences of living for years or generations in such a setting, because no human community has done it. Would bones and muscles adapt into a new stable baseline, or continue degrading? Would cardiovascular systems settle into a viable norm, or carry hidden long-term costs? Even before we leave the solar system, gravity is already forcing hard questions about what kind of life away from Earth is biologically sustainable. For exoplanets, the uncertainty is even greater, because in many cases we do not know the exact composition well enough to infer the surface environment with confidence. A planet's mass may be estimated, its radius may be measured if it transits its star, but translating those numbers into lived reality is far from straightforward. A large radius with a relatively low mass might imply a thick envelope of gas or volatile materials, meaning there may not be a solid surface in any familiar sense. A smaller radius with higher mass could imply a dense rocky world with intense gravity. In other words, when people say a planet is Earth-sized or super-Earth-sized, they are often standing at the edge of a much larger unknown. And gravity does not operate alone. It interacts with atmosphere, temperature, and planetary structure in ways that shape the whole experience of a world. A stronger gravity can compress the lower atmosphere, potentially affecting pressure profiles and weather. It can influence mountain height, ocean behaviour, and how particles settle through air. Combined with a dense atmosphere, it could make movement even more difficult than gravity alone would suggest. Combined with heat, it could turn exertion into something oppressive and exhausting. A world might look stable in a remote dataset while feeling physically crushing on the ground. This is one reason the phrase habitable planet needs constant discipline. Habitable for telescope catalogues is not the same as habitable for explorers, settlers, or anything like ordinary human life. A world may support liquid water and still be a place where the human spine, circulatory system, and metabolism are under relentless strain. Another may have mild gravity, but no magnetic protection. Another may have a good atmosphere and terrible radiation. Another may be geologically stable, but tidally locked into harsh climate extremes. The more seriously we imagine setting foot somewhere, the more the word habitable begins to divide into categories. Habitable for chemistry, habitable for microbes, habitable for ecosystems, habitable for us. That final category is far smaller than the others. It may require not just a rocky planet in a favourable orbit, but one with a breathable atmosphere, manageable radiation, long-term climate stability, liquid water, and gravity close enough to Earth's that the body is not pushed into chronic stress. That is a remarkably demanding combination. We should not assume it is vanishingly rare, but neither should we pretend it follows automatically from a few promising measurements. The body is a harsh judge. It will not be persuaded by optimistic headlines. In a strange way, this makes Earth feel even more intimate, not just because it has oceans and air, but because it fits us physically at every moment. The distance your blood must travel, the load your knees can bear, the way your muscles develop, the way balance works when you walk across a room, all of it has been shaped under one very specific gravitational condition. We are not simply inhabitants of a planet, we are products of its exact pull. Move too far from that pull in either direction, and the ordinary becomes difficult. Move far enough, and it becomes impossible. That is why the search for other worlds cannot stop at broad categories and hopeful names. A planet's true nature is hidden behind the methods by which we detect it. We do not start with beaches or mountains or skies. We start with wobbling stars, dimming light, and tiny shifts inside noisy data. Everything else comes later, cautiously, if it comes at all. And the fact that we can infer so much from such faint traces is one of the great achievements of modern astronomy, even if it also means the universe often reaches us first as an uncertainty. By the time we begin talking about atmospheres, gravity, or life, it is easy to forget how little we actually start with. We do not usually begin with an image of a planet. We begin with disturbances. A star is not where it should be. A brightness pattern changes by a tiny amount. A spectrum shifts almost imperceptibly. Somewhere inside that faint behaviour, a planet is implied. That is the remarkable thing about exoplanet science. We have learned to detect worlds we cannot properly see by watching what they do to the light and motion of their stars. This is necessary because stars are overwhelming. A planet may be enormous on human scales, but next to its parent star it is dim, small, and hard to isolate. Even in the nearest stellar systems, directly photographing a planet is extraordinarily difficult. In most cases, the star floods everything nearby with light, washing out the far fainter world orbiting beside it. If directly looking for the planet fails, then astronomy has to become indirect. It has to infer the unseen from its effects. That is why exoplanet detection often feels more like listening for a hidden mechanism than taking a picture of an object. The first major breakthrough came through motion. A planet does not simply circle a star while the star stays still. Both bodies orbit their shared centre of mass. The larger object moves less, but it still moves. That means a star with a planet can wobble ever so slightly in response to the planet's gravity. If that motion happens partly toward and away from Earth, astronomers can detect it as tiny shifts in the star's light spectrum. Light moving toward us is compressed a little. Light moving away is stretched a little. This is the radial velocity method, sometimes called Doppler spectroscopy, and it was one of the first great tools that opened the exoplanet era. Its power lies in precision. Astronomers do not need to see the planet itself. They only need to measure the star's periodic motion with extraordinary care. A more massive planet causes a stronger pull. A closer planet causes a quicker rhythm. That is one reason the earliest discoveries were often giant planets in tight orbits, the so-called hot Jupiters. They were not necessarily the most common planets, they were simply the easiest to detect because they tugged on their stars more strongly and more often. The first confirmed exoplanet around a Sun-like star, found in 1995, belonged to that category and changed astronomy almost overnight. But radial velocity also has limits, and those limits matter because they shape what kinds of worlds appear in our catalogues first. Small planets are much harder to detect because the wobble they induce is far weaker. More distant planets also create longer signals that require more patience and cleaner data. And active stars complicate everything. A star with flares, spots, and magnetic turbulence can produce its own apparent shifts, making a planet harder to isolate from stellar noise. That is exactly why Proxima Centauri has been such a demanding target. Detecting something like Proxima d required finding a wobble so small that for a long time it would have been effectively invisible to our instruments. That is what makes the discovery of tiny nearby exoplanets such a technical milestone. It is not just that another world was found. It is that the precision of the method reached deep enough into the noise to reveal a signal once thought too faint to trust. And yet trust is always conditional. A weak signal can be genuine. It can also be an artifact of the star or the instrument. This is why confirmation matters so much. Proxima c, for example, remains a lesson in scientific caution. One analysis can suggest a planet. Another can question whether the same pattern might come from subtle calibration issues or from stellar behaviour that only looks planetary at first glance. Exoplanet science advances by detection, but it survives by skepticism. The second major technique transformed the field even more dramatically because it was so well suited to scale. This is the transit method. If a planet's orbit happens to be aligned so that it passes between its star and our line of sight, then the star dims by a tiny amount during the crossing. That dimming repeats each orbit. Measure the regularity of the dips and you get the period of the planet. Measure how much light is blocked and you begin to infer the planet's size. It is a beautifully simple idea in principle. In practice, it requires extraordinary sensitivity because the change in brightness can be minuscule, especially for small planets. The Kepler Space Telescope turned this method into a revolution. Rather than examining one star at a time in a narrow and targeted way, Kepler watched a huge field of stars continuously, searching for these periodic dips in brightness. It stared and waited and recorded. The numbers it returned changed the scale of the entire conversation. Before Kepler, exoplanets were still precious discoveries. After Kepler, they became a vast population. Thousands of confirmed worlds emerged, with thousands more candidates awaiting further study. And perhaps even more important than the raw count was the implication. Kepler looked at only a tiny portion of the sky. If that small patch contained so many planets, then the galaxy as a whole had to be rich with them. Transit detection also gave astronomers something radial velocity alone could not always provide as cleanly: planetary radius. Once you know how much of the star's light is blocked, you can estimate how large the planet must be. Combine that with mass information from radial velocity when available, and you start to infer density. That helps distinguish a rocky planet from a gas-rich one. A world with Earth-like size but suspiciously low density may not be a terrestrial surface at all. A somewhat larger planet with high density may be genuinely rocky. In other words, the transit method did not just multiply discoveries, it deepened the physical interpretation of those discoveries. But transit astronomy has its own built-in bias. Most planets will never transit from our point of view, because their orbital planes are not aligned just right. Even in systems that do host planets, we may see nothing, simply because the geometry is unfavourable. That means every transit survey is looking through a powerful selection effect. The planets we detect this way are only the ones whose orbital arrangement happens to expose them to us. Larger planets are easier to find because they block more light. Closer planets transit more often, so their patterns emerge faster. Smaller Earth-sized worlds on wider orbits are much harder to catch. This is why translating detections into true galactic populations requires careful statistical correction. The next generation of missions built directly on that foundation. The Transiting Exoplanet Survey Satellite, or TESS, expanded the search across a much larger portion of the sky, especially targeting stars nearer to Earth than many of Kepler's. Its role has been not just to discover, but to identify promising candidates for deeper follow-up. Then there is CHEOPS, the Characterizing Exoplanet Satellite, which took an even more focused approach. Rather than sweeping broadly for unknown worlds, it was designed to study known exoplanets in greater detail, especially smaller planets where precision matters enormously. In a sense, this marks the maturation of the field. First you find planets in quantity, then you refine, characterize, and ask what those planets are actually like. There is something almost poetic about how indirect this work remains. Cheops, for example, does not need a sharp cinematic image of a planet to do useful science. In fact, some of its observations look deliberately blurred because the mission is not trying to make a pretty picture. It is trying to distribute starlight across detector pixels in a stable way so that tiny brightness changes can be measured more accurately. To a casual observer, that may seem counterintuitive, a blurry star helping us understand a hidden planet better than a sharp image would. But that is the logic of exoplanet astronomy. Clarity does not always look like clarity. Sometimes the best path to truth is not a picture at all, but a cleaner measurement of light. And from light, an extraordinary amount can follow. During a transit, a tiny fraction of starlight may pass through the planet's atmosphere before reaching us. If certain wavelengths are absorbed more than others, astronomers can begin to infer what gases are present. This is spectroscopy, and it is one of the most powerful tools in the search for habitability. Oxygen, water vapour, carbon dioxide, methane, sulfur compounds, all of them leave different patterns in the spectrum. Not proof of life by themselves, but clues. Clues to chemistry, temperature, climate, and perhaps in the future, biological activity, or at least chemical disequilibrium that begs for explanation. This is where the field becomes especially delicate, because the public imagination often wants certainty faster than the data can deliver it. A hint of water vapour becomes a headline. A spectrum suggesting one molecule becomes a burst of speculation. But atmospheric characterization is difficult, easily affected by noise, clouds, instrument limitations, and interpretation. Most exoplanets are still far beyond the level of certainty we would want before making grand claims about life. What we often have are suggestive fingerprints, not panoramic understanding. Yet that does not make the work less extraordinary. It means the frontier lies precisely in this tension between faint evidence and enormous implications. There are other methods too. Astrometry measures tiny changes in a star's position on the sky, another sign of gravitational tugging. Direct imaging, though rare, can sometimes isolate young or massive planets far from their stars. Gravitational microlensing can reveal planets through the way their gravity briefly magnifies the light of a more distant background star. Each method has its strengths, its blind spots, and its preferred kinds of worlds. Together they form not one instrument, but a toolkit for interpreting the invisible. What emerges from all this is a humbling truth. The worlds now filling our catalogues did not first arrive as landscapes. They arrived as periodic dips, spectral shifts, wobbling stars and contested signals. We know that planets are abundant because the evidence has become overwhelming. But for most individual worlds, our knowledge is still thin. A mass here, a radius there, a rough temperature estimate, a possible atmosphere, a maybe, a likely, a candidate, a confidence interval. Public imagination tends to see the count of discoveries and assume the mystery is shrinking quickly. In fact, the opposite may be happening. The more worlds we find, the more different they become from one another, and the more careful we have to be with every claim. That is why the current era is so intellectually exciting. We are no longer asking whether planets exist around other stars. We are asking what kinds of planets are common, which stars make good hosts, how atmospheres survive, how chemistry evolves, and how often all the right conditions line up for long-term habitability. We are also learning that the methods themselves shape the answers. A world can remain hidden simply because it does not transit. Another can seem dramatic because its signal is easier to measure. Absence of detection is not absence of existence. Presence in a catalogue is not full understanding. And behind all of it sits the same unresolved question that gave the search its emotional force in the first place. Somewhere among these worlds, is there one that is not merely statistically promising, but truly alive? We do not yet know. Our instruments are becoming finer, our catalogues deeper, our atmospheres more measurable, but the distance between detection and certainty remains enormous. That is why every new method matters, every improvement in precision matters, every future telescope matters. Because the galaxy may already be offering up billions of candidates, and yet the difference between a possible world and a proven living one is still one of the greatest gaps in science. That gap is what makes the final scale of the search so difficult to hold in the mind. On one side, we now have enough evidence to say that planets are a normal feature of the galaxy, not rare exceptions, not strange accidents, normal. On the other side, we are still struggling to identify even one world beyond our solar system that we can confidently call truly Earth-like, let alone inhabited. Those two facts coexist. The Milky Way may be full of planets, perhaps full of rocky planets, perhaps even full of worlds sitting in zones where liquid water could exist, and still leave us unable to answer the oldest question with certainty. Part of the difficulty lies in the sheer number of filters between a promising orbit and a living world. A planet must form. It must survive the violence of its system's early history. It must gather and retain the right materials. It must avoid losing its atmosphere or boiling away its water or freezing permanently, or collapsing into climatic extremes. Its star must not be too unstable. Its chemistry must remain rich enough, long enough, for complexity to emerge. And even then, life itself is not guaranteed. We know that life arose on Earth, but we still do not know exactly how likely that transition is under favourable conditions. The universe may produce biology readily, or it may require a chain of events so improbable that even a galaxy full of planets yields only scattered examples. This is why estimates about habitable zone worlds, however exciting, always need care. Depending on the assumptions used, astronomers can arrive at very large numbers for how many potentially temperate planets may exist in the Milky Way. There may be billions. But potentially temperate is not the same as inhabited, and it is not even the same as human compatible. A habitable zone count is a first approximation, a way of marking where conditions might be favourable if many other things also go right. It is useful. It is not a conclusion. The phrase can point us toward good targets, while still hiding how many of those targets may turn out to be dry, airless, irradiated, frozen, overheated, or biologically empty. In that sense, the exoplanet revolution has done something subtle to our understanding of life in the universe. It has made the question feel both more open and more demanding. More open because the old fear of cosmic emptiness has weakened. There are simply too many worlds for us to maintain the older image of planets as rare jewels. More demanding because with every new discovery, the standards for evidence become higher. It is no longer enough to find a rocky planet in a favourable orbit and let imagination do the rest. We want atmospheres. We want chemistry. We want long-term stability. We want signs that the planet is not only there, but functioning in a way that could sustain complexity. That is where the future of astronomy becomes so important. The next great advances will not come only from counting more planets. They will come from characterizing them more deeply. Larger telescopes, more sensitive spectrographs, space observatories optimized for atmospheric study, and more refined methods of suppressing starlight will gradually turn some of today's distant hints into richer portraits. We may begin to detect atmospheric patterns with greater confidence. We may identify combinations of gases that are difficult to explain without active replenishment. We may learn to distinguish barren rocky worlds from ocean-covered ones, or thick shrouded atmospheres from thin exposed surfaces. None of that will happen instantly, and none of it will erase uncertainty completely, but the direction is clear. Astronomy is moving from discovery toward diagnosis. That transition matters because the first era of exoplanet science taught us abundance. The next era may teach us quality. Which stars make the best long-term hosts? Which planets hold on to atmospheres? Which combinations of mass, orbit, and stellar type most often lead to stability? Which apparent candidates repeatedly disappoint, and which categories begin to look more promising over time? The answers will reshape not only the scientific search for life, but the philosophical one as well. Because hidden inside every technical result is a larger human question. Are we living on one example among many, or on something rarer than we once believed? The irony is that the more carefully we search outward, the more our own world comes into focus. Earth used to feel cosmically ordinary because it was the only example we had. Then for a time it risked feeling cosmically generic because the phrase Earth-like spread faster than the evidence supporting it. Now a more balanced picture is emerging. Earth is neither obviously unique nor casually replaceable. It sits in a harder category than many of us once assumed. Not impossible, not magical, but exacting. A planet with surface water, a protective magnetic field, long-term climate moderation, a breathable atmosphere, suitable gravity, and billions of years of relative continuity is not merely a rock in a habitable zone. It is a system that succeeded across many tests at once. That does not diminish the search for life elsewhere. It deepens it. If Earth-like worlds are difficult to make and keep, then every one we eventually find will matter more, not less. If life turns out to be rare, then its discovery elsewhere will be even more profound. If life turns out to be common, then the path by which the universe reaches it may be one of the great general principles hidden in nature, something as fundamental as star formation or chemistry itself? Either answer would transform how we see ourselves. Either answer would justify everything this search has already demanded. And still, for now, we remain in the age of inference. We know enough to say the galaxy is crowded with possibilities. We do not yet know which of those possibilities are real in the deepest sense. Somewhere out there may be oceans moving beneath alien winds, weather crossing continents we have never seen, chemistry edging toward biology under another sun. Somewhere there may be nothing but silence, stone and sterile sky where our models once suggested hope. Both remain possible because the universe has given us numbers faster than it has given us understanding. That is why the nearest worlds matter so much. Proxima b matters not because it has been confirmed as a second Earth, but because it is close enough to force the question into practical focus. It is a world we can imagine studying more deeply, perhaps even reaching one day with machines. It turns abstraction into destination. It also reminds us how easily hope can outrun evidence. The nearest potentially temperate planet may already be showing us the limits of our assumptions, the danger of easy labels, and the harsh reality that many promising worlds are shaped by stars far less gentle than our own. So the search continues in two directions at once. Outward, toward more planets, better instruments, and finer measurements. Inward, toward a more disciplined definition of what we are really looking for. Not just any planet, not just any habitable zone, not just a world with roughly the right size or temperature. We are looking for a place where matter did not merely assemble into a planet, but into a durable environment, one stable enough for complexity, perhaps for biology, perhaps even for minds. That is a narrower target than our earliest optimism suggested, but it is also a more meaningful one. And perhaps that is the most powerful shift of all. The exoplanet revolution has not simply multiplied worlds, it has changed what Earth means. Our planet no longer stands alone in a sky empty of comparison, but neither does it disappear into a blur of easy substitutes. Instead, it sits within a universe that appears rich in possibility and severe in its demands. Billions of worlds may circle the stars of the Milky Way. Some may indeed resemble Earth in the ways that matter most. Life may have emerged many times, but until we can close the gap between candidate and certainty, the rarest thing we possess is not the dream of other worlds. It is the one world we already know can carry life through the dark.